Hi everyone and welcome back. In this video, we're going to talk about the system design of the coding contest platform, something like Leetcode or Codeforces. We're going to start out by talking about the main data objects and how we store them. We'll talk about the database schema and design. Then we'll touch based on the asynchronous code execution, CDN, and the leaderboard. Was that? Let's get to the video. Before we start talking about the system design and the workflow, let's first define the main data entities that we're going to deal with. And in the example of the gate code, for instance, the user opens up a problem. As you can see on the left here, this is the first screen that the user sees. And what kind of data it consists of? First, we have a prompt. Prompt was the problem that is written in the text, and that data can be stored simply as a text file somewhere. Then we choose a language, and we have a language template. So those templates also static and ideally can be stored somewhere, perhaps in the CTN. Then we have a test cases. So for every single problem, we'll have two types of the test cases. The first one is a sample test cases and results when we just click a run button. And the second one is a submission test cases and results, where we'll have many more test cases with the results against which our solution will be evaluated. So all these data pretty much static, and it can be stored somewhere in the static data store. For instance, it can be an object store. As you can see on this diagram, in the left side, we have a user who opens up a problem. Here, we need a data storage for our problem metadata and actual prompts. Since we want to build a global system and provide similar latency for every user that accesses the problem, whether it's in the United States or Asia, we want to make sure that these static files stored somewhere perhaps in the CDN, since they are static, and served from the region where the user is. For instance, if we are in Australia, then we're going to download those problems from the CDN data location that is located in Australia, or United States or India, etc. But to do that, we need to know either the ID of the problem or a link on where it's located. So for this, we'll have a problem metadata DB. So as you can see on the diagram, we first reach out to the problem service. This is the service that has access to a metadata database for all the problems. Over there, for every single problem, we'll have an ID and we'll have links or locations for the prompts and test cases and all the static files that this problem has. Then once we get a link on where the problem can be downloaded from, we simply reach out to that link and download the problem from the CDN. With this design, we have a lot of flexibility because if we know where the user is located, we can provide the specific link that is closest to the user's location. For instance, if I'm in Australia and I want to see the problem, then the link that's going to be returned to the user will be a link to the CDN in Australia, not the one in the United States. And then if the user changes the location, for instance, one can either change it in a static field on his profile, but he's now located in a different region, or we can also implement a dynamic latency-based serving for the user where the link to the prompt that is returned from our service will be returned based on the latency from the user location to the closest CDN. When we talk about the database implementation, the problem metadata database would likely be implemented by NoSQL database, just because we can simply partition it by problem ID. As you can see on the schema in purple, problem ID would be a partition key, and then the rest of the columns would be just informational key. And this way, this database can be first highly available, and the second, since the data is static, and also going to be actively cached. And instead of calling a NoSQL database, we can just retrieve the most recently opened problems from the Redis cache. And in the CDN service, for that, we might be using the public CDN from Cloudflare or someone else. And that service would be backed by our problem object store, where the problems, prompts, and files would be stored. It would be something like S3 or any other object store. With this design, we can scale the system globally and provide the same low latency for every single location. For instance, from the deployment perspective, we would have two big components. The first one would be a core deployment, which would consist of our problem service, submission processor, databases, and the core business logic. It can be deployed across multiple continents. We can say America, Europe, Asia, Australia, South America. And then for the CDN, we would have a more granular location. We would have, for instance, if in America we would have a single site deployment, then for the static content, we would be able to download it from, let's say, 5 or 10 different locations in the United States, 10 more in Europe, Asia, etc. With this approach, we can have, let's say, 5 or 6 core deployment of the service around the world, and then we can utilize hundreds of CDN locations for the caching of our static content. So for every single user, it would take 2 calls. One call would be to declose a core deployment to retrieve the links that have to be used for downloading the problem prompt. And then the second call would be to declose a CDN that would also have very low latency. So everyone around the world would have a very similar latency to open up a problem. Now let's go to the second code feature, which is asynchronous code execution and providing results for the user. We want to implement 2 things. We want this process to be asynchronous because we can tolerate traffic spikes and be able to process all the submissions. So for this, we would have the following workflow. As we write some code in the Leetcode, for instance, in the browser, we click either the Run button or Submit button. So there are 2 different use cases. Let's say we click a Submit button. So what happens here is that we send the written code and ID of the problem, user ID perhaps, to our submission processor. This service does 2 things. First, it stores our code that we sent and through the submission service. This code gets stored in the submission object storage and metadata DB. And then once the code is stored in our submission databases, submission service returns the ID or location of that submission to a submission processor. Now submission processor creates a message that would have a ID of the problem, ID of the code that was submitted, and one sends that message to the Kafka queue. On the other side of the Kafka queue would have submission task routers. And these would be a pool of workers, or it can be Docker containers in the pool, or it can be virtual machines in the auto-scaling or node pool in AWS, for instance. A lot of small instances that would receive a message from the Kafka and then execute the code against the test cases and return the result. So here, every single task writer will get a message that would contain all the IDs of the execution. So one would need to first download the code from the object storage. Then one would download the test cases and results for this code and then execute them on the machine. Once the code is executed, the result would be sent to the submission service and stored again in the object storage. And once the results are stored, the task runners, which is keep taking out more messages from the Kafka and keep executing. Here, we want to make sure that our task runner pool is auto-scalable based on the Kafka queue, for instance. So if the number of messages in the Kafka queue keeps increasing, then we would probably want to spin up more task runners just so we can catch up with the workload, and the user and the customer would get the result of the code execution in time without long waiting. There are more features we can implement here. For instance, we can have different queues for paid and free users. So paid users would be prioritized first, and then the free users would have some sort of, let's say, longer time execution or perhaps some rate limiting for the task execution. So all these features can be implemented with this approach. Now going back to the task runner, once the job is done and the data is stored, submission service would form a metadata for this code execution, send it to the submission processor, and then submission processor would have some sort of server-side events, perhaps with the client, and send the result of the execution with all the IDs on where the detailed information stored to the user. And the user will see the result that, for instance, this test failed. And then if one clicks the link, they use the ID that was returned back to the user to open up a submission result from the submission object store. Another use case here, if the user puts his own test case in the browser for the problem and sends it to the server. This way, there is no way for us to compare those test cases against predefined results. For this use case, you would need to pass the custom test cases with the code submission, store them in the submission service. Then we need to download a predefined code solution for the problem, run the custom test cases against the code solution, and then execute the user's code for this problem, and then compare the results. So there are a few more steps for the code execution. That's why you can't provide, let's say, hundreds or thousands of custom use cases from the Leetcode, because it would add up time for execution. We can only put, I don't know, 5, maybe 10 custom use cases, which in the end of the day doesn't really add up that much time for executing the code multiple times on the same task runner. From the database design perspective, as you can see here on the diagram, we would have a lot of submissions because every user would submit different problems. So for the schema, we would have a user ID, problem ID, submission ID. We would have a timestamp, submission link. These are the required fields for the submission record. And the database, we can have a NoSQL database implementation here as well. And the way we would partition it, as you can see here, we would have a partition key in purple. It would consist of user ID and the problem ID. And the reason why, because first we want to make sure that all the submissions for the same problem are located in the same place on the same server under the same partition. And this way we can have, if we want to retrieve, let's say 5 or 10 different submissions for the same problem, we can do it simply in one request. And at the same time, user ID and problem ID provides us a unique ID that can be evenly distributed across multiple nodes, and we wouldn't have any hot partitions with this design. Now let's talk a little bit about the leaderboard. And for here, I have a separate video where I talk about the leaderboard implementation, but bottom line for this problem, we would have a contest service that would be responsible for maintaining the metadata about the contests, users, information about the users that participate, time that the contest start and end, etc. All that metadata will be in the database behind the contest service, and that we would need the leaderboard that gets updated in the real time as the contests go on. Usually for the platforms like Leetcode, it's not actually in the real time, it just gets micro batching, where we would just have a MapReduce job that would run against all the submissions and then filter all the submissions for the specific contest, group by user, and provide all the details that are needed for the leaderboard. From the database design, our leaderboard would look something like this. As you can see on this diagram, we would need to use a contest ID as a partition key. This way, all the data about this contest would be stored under the same partition. And the way to optimize it is that we make rank as a sort key. This way, for every single contest, we would have a sorted users by rank. And when we open a leaderboard, let's say we have 20,000 people participating in the contest, we don't need to retrieve all those users' ranks. All we need to do is just retrieve the top 10 or 20 users' ranks to show the first page, and then as we paginate, we can just provide additional requests to our database to retrieve a specific range based on the offset. But the problem here is that our table would need to be updated regularly, let's say every 5 minutes. And if we use a contest ID as a partition key, then we would need to pretty much rewrite all the data, because our contest ID as a primary key, we would need to create a lot of tombstones. So I think in this case, the better approach would be to use a SQL database for our leaderboard and make sure we do updates in a place. This way, in the real time, we have up-to-date data that can be returned back to the client. And if we use 20,000 or 100,000 users per the contest, it's not that much data for the specific contest. We can simply have a user ID as a primary key, and let's say we can have indices on the contest ID and rank, which will speed up our retrieval, which will allow us to do a pagination of the database. But the leaderboard, the data that is returned back to the client, can be stored in the SQL database. So the process would be the following. We would have a ranking MapReduce job that would retrieve all the submissions, let's say every 5 minutes. Then we would perform a list of operations on filtering and mapping. In the end, we would get a result where we'll have a list of problems with their solutions grouped by a user. And then that data would be first stored in our SQL leaderboard database. So all the previous data would be overwritten with the new data. And then the second, if we want to maintain a history about every single Java execution, and then perhaps look back and see the progress of every single person and the progress of the contest, on what problems were solved, we can store the results of this execution to a NoSQL database. and maintain a history of all the executions throughout the contest. And if we use NoSQL database for storing the history of the executions through the contest, let's say every 5 minutes we have a new execution. This way we have to have a partition key, a contest ID, so we can always find all the data that belongs to the specific contest. And then for the sorting ID, we can try to have, let's say, a timestamp perhaps. This way we can retrieve a results for execution for every single timestamp and then process it further. At the same time, we would not be using the historical database for any real-time data rendering to the user. We would be using SQL database because our history database is not optimized for retrieving that data. It will only be optimized for retrieving a whole snapshot of the results for a specific contest at the specific time. So this is how we would implement a coding contest platform. If you found this video useful, make sure you like and subscribe to my channel. Check out my system design course, and I'll see you in the next one. Bye.